Alrighty, so last time we did in 11B sampling without replacement. Now we're going to do sampling with replacement. So that's something like tossing a coin, rolling a dice. What happens on the first go doesn't affect what happens on the second go. They also use it for large populations. So if you drew a random person out of Melbourne and then you went and drew another person out of Melbourne, it would be very unlikely the same one. So a large population is all right. So what we're going to do is look at the example of rolling a dice or a die, and our random variable is going to be the number of threes. So when I roll my dice, so we're going to do it, sorry, 3 times. So when I roll my dice 3 times, what happens? I can get a 3 or I can get not a 3 on the first go. When I roll it the second time, it'll be independent. I can get a 3 and not a 3. A 3 and not a 3. And then I roll again. Guess what I can get? 3, not a 3. So my outcomes are 3, 3, 3. 3, 3, not 3, not 3. 3, not 3, 3, etc. All right, so the number of threes, so this would be x equals 3, because we've got 3 threes. This would be x equals 0. This would be an x equals 2, etc. All right, so it's sort of similar to a coin toss, but they're all not going to be 50-50. So if I go and think of the values, getting a 3 is 1 out of 6. Not getting a 3 is 5 out of 6. So without, I'll just fill in these values. So this one, x equals 3, would be 1/6 times 1/6 times 1/6, or 1/6 cubed, which is 1 on 2 1/6. Down the other end, I can't fit it on the screen, but it'd be 5/6 times 5/6 times 5/6, which is 125 on 2 1/6. Now, all the ones that are a, what have we got? T, not. So all your x equals 2s, they're 1/6, 1/6, and 5/6. And we can get that 1, 2, 3 times. So this will end up being x equals 2. Each of them is 5 on 2 1/6, but we'll get 3 of them. And the way of getting 1, it would be 5/6 and 1/6 and 5/6. So 3, not. So with those ones, they're 25 on 2 1/6, and there's 3 ways of getting that. Okay, so we're trying for this not to be tedious, but it does take a little bit of writing. So if I want to put that as a probability distribution, and remember we said we've got x and probability that x equals x. So the probability that x equals 0, probability that x equals 1, 2, or 3. So I know for 3 it was 1 on 2 1/6. This was 125 on 2 1/6. And for the 2s, we've got the 5, 10, 15. And then with the 1s, we add up, there'll be 75 on 2 1/6. Because we had 25 and then 3 times, okay? So that's an example of sampling without replacement. That took a long time, didn't it? And that's only doing 3 trials. What would happen if we did, say, 5 trials or 6 trials? So you know what? The mastery of math, the best thing ever, is someone went and worked out how we can do it as a formula. So if you want to think about what we did last time, the probability that x equals 0, x equals 0, how many ways could that happen? Well, it can only happen one way, because it was this way, not. So what you can do is write that as 3 choose 0 or 3C0. On your calculator, you'll get NCR and you type in 3, 0. And if you do that, it gives you 1 because there's one way of choosing no 3s. So what about if we had, sorry, it's not probability. If we had, what about how many ways are there of getting X equals 1? 3 choose 1 or 3C1 on our calculator, NCR 3, 1, and it gives us 3. Obviously it does because when we worked it out there was 3 different ways. That's why it was 25 over 16 and we had 3 of them. So let's have a guess. If it was X equals 2, 3, 2? Yep, you guessed it, it's 3. What about how many ways can you choose 3? Well, the only way was not. So that's equal to 1. So that's how we can find out how many ways we can choose those by using the combinations that we did yesterday. So what's this called? Sampling with replacement. So when we do with replacement, we call it a binomial distribution. And for something to be a binomial distribution, binomial 2, there's 2 outcomes and we call them success or failure. So in this case, getting a 3 was a success, not a 3 was a failure. So the probability of success we say is P. So the probability of failure is 1 minus P. And we also know that they must be independent to be a binomial distribution. So independent, we've got replacement, because what happens on the first go doesn't affect what happens on the second go. So if you think of our example we did with the 3s and not a 3, if I wanted to find the probability that X equals 1, what I do is I say 3 choose 1 times by the probability of success, which is 1 out of 6. And I do that to the power of 1, this number here. And then the other one, 5, 6, but I do that to the power of 2 because I go 3, take 1. So if you work this out, 3 choose 1 was 3 times 1 on 6 times 25 on 36, you would get 75 on 216, which is what we got in our table. If you wanted to do the probability that X equals 2, you would go 3 choose 2, success to the power of 2, failure to the power of 3 minus 2. And if you work that out, you're going to get what we got in our table, 15 over 216. Right, so let's have a think of what this might look as a general formula. For a binomial distribution with n trials. So we had 3 trials, but if you had n trials, you say it's n choose X, and X changes each time, whether it's 1 or 2 or 3. And then you do the probability of success to the power of X times the probability of failure to n minus X. And that will give you the answer every time, so you don't have to worry about drawing a tree diagram if this number was quite big.